Okay, so in this problem, it says that we have a population mean of 40. I'm just going to write that down. The population standard deviation is 5. What's the likelihood that a task takes over 45 minutes? So that's just a normal distribution. It did tell us that. Normally distributed. We have a mean of 40 and a standard deviation of 5. And we wouldn't know the likelihood that someone takes more than 45. Okay, so this is just like a problem we could have had on exam 1. We're going to get that distance between the mean and this point over here, this 45, and we're going to express that in standard deviation units, or z. So we take x minus mu over sigma, and that's equal to 45 minus 40 over 5 is equal to 1. We know that goes with, or you can look it up, that's 3413. That's this area. So the area out here is 0.5 minus that, 1587. So is the answer. On number 2, we still have a population mean of 40. We still have a population standard deviation of 5. We still have a normal population. But now we have a sample size of 4. And our question is, what's the likelihood that the sample mean is over 45? So that means we're asking about sample means. This is a sampling distribution of x bars. The mean of the x bars is equal to the mean of the population. That's 40. And the standard error of the x bars is equal to the population standard deviation divided by the square root of n. So that's 5 divided by the square root of 4. And that's 2.5. And now, we're asking about sample means. We want to know the likelihood of getting a sample mean that is above 45. So to this point, really all that's changed is our labeling. That it's a distribution of x bars. That it's the mean of the x bars. That it's the standard error of the x bars. So now when we go to work our problem, it's going to be just like the previous one. We're still looking at z, but now it's the number of standard errors from the mean. But it's x bar minus the mean of the x bars instead of x minus mu. But that is our random variable minus the mean of our random variable divided by the standard error of our random variable. Remember, in this case, it's the mean that varies from sample to sample. If we were to take many samples, sometimes you would get, if the mean really were 40, sometimes you'd get 40, sometimes you get 41, you would get different things there. 45 minus 40 over 2.5 is equal to 2. That goes with 0.4772, and 0.5 minus that is 0.0228. So this area here is 0.0228. Okay. So that's just computing probabilities under sampling distribution. That's a fairly straightforward jump from what we did on exam 1. All we had to do was move from the random variable x to the random variable x bar and correct on the standard error by dividing the standard deviation by the square root of n. This is just another computing probabilities with a sampling distribution. So the population mean is still going to be 40, and the standard error, which we computed in the previous part, well, it won't be the same here. We have a random sample of 16. Maybe I will just, this is a good practice. Write the population mean down. The population standard deviation is equal to 5. We have a normal distribution. We're asking about sample means, so we're asking about the distribution of sample means. We want to go from 38 to 42. So we're going to have to get that area and then get that area and add them. But we need the standard error let's see, we have a sample size of 16, and we need the standard error for this sampling distribution of x bars. The sigma that we have here would be at the random variable was just x, but we're not asking about x's, we're asking about means. So this is equal to sigma, the standard deviation, divided by the square root of n, or 5 divided by the square root of 16 is equal to 1.25. From here, other than using x bars instead of x's, it's the same problem we did on the last test. So I'm going to call this area A. That's x minus mu, x bar minus the mean of the x bars over the standard error of the x bars. 38 minus 40 over 1.25, and that is 1.6. Area for that is 0.4452, just looking on the z table. And now I'll get area B. When I get that one, we'll just sum them together and have our answer. Now it's 42 minus 40 over 1.25. That's, by the way, that one up there should have been minus 1.6. It's still 44.52, but should have been minus. This one is positive 1.6, which is also 0.4452. So we have 4.552 here, and another 0.4552 there. Add those together, and you should get 8904. What I am going to do is I'm going to do part number 5 before I do 4, since there's a number in 5 that we will use, that we can use when we get to 4. We have a manager who thinks the population mean should be 40 minutes. That's a question, really. The population standard deviation is 5. He knows how the process works. It's normally distributed. N is 16. X bar is 45. Is this enough evidence to conclude that the population mean is over 40? And that could have been something we had on exam 1, is the population mean greater than 40. Here's what's different now, is we're going to pair that research hypothesis with what's called a null hypothesis, which just means the hypothesis of no difference. So that'll always be equal there. You'll see some books that in this case would put it less than or equal, but when you really are doing the test and computing probabilities, it's based on HO with mu equal to 40. Okay, so that's part A, right? The hypotheses, the research hypothesis. Some books call that the alternative hypothesis, and in HO, the null hypothesis. So perform a hypothesis test using the critical value approach. Basically how this works, we really won't draw the picture. We'll use some tables and look things up, but just so you'll know how it works, we have our hypothesized mean here, which is 40. That's from HO. When will we reject, if we get 40.1, would we say is mu is greater than 40, or could it have just been sampling error? That might have been sampling error. Or maybe it's so tight that it wouldn't be. What if we got 50? What if we got 60? Exactly when would we start saying that we have enough evidence to conclude the population mean is greater than 40? Well, it's going to be over here somewhere. And we're setting up a cutoff of 0.05, so it's when that probability is 0.05 or smaller. Anytime you get a probability less than 0.05, you'll be out there. We're going to compute a critical value here, a z that says how many standard deviations above the mean before you reject HO. So I've prepared a little table for you. If you haven't printed it out yet, it's just a one-page table called Common Z Values. If you look on there, it has some cutoffs, like 0.05 is one of them. It says one-tailed or two-tailed. Well, in this particular problem, we have a one-tailed in the upper hand side because we want to show that the mean is greater than 40. So when are we going to conclude that it's greater than 40? When we get a value above here, we'll call that the rejection region. As opposed to anything below here, which is where we would fail to reject HO, starting here. So what is this z-value? Well, if we have 0.050 here, that's 0.45, and if you look that up in the center of your z-table, or better yet, you use the table of common z-values that I gave you there, you should find that that z-value right there is going to be 1.645. So now I'm coming to part B. I'm going to reject HO if z-test is greater than 1.645. The z-test is equal to the statistic x bar minus the hypothesized mean. So it's this distance right here divided by standard error. So basically, this point that we have, in this case, the point that we have wherever it is we're going to find out how many standard errors above the mean that is. So here we go. We have 45 minus 40 divided by, now our standard error, put that over here, is equal to sigma divided by the square root of n, or 5 divided by the square root of 16 is 1.25. So that's 1.25. And when you compute that all out, you should get 2.4, which is greater than 1.645. So you do reject HO. There it is. It's rejected. And you conclude, because it's the only thing left, that the population mean is greater than 40. That's basically, I guess, part of the logic of hypothesis testing is, here's what we want to conclude, so we put its opposite here and try and reject it. Maybe write down for yourselves that the z-test is 2.4. We can use that on the previous problem, on problem 4. That's where I'll go now. So just coming back here, I'm going to go ahead and just label this sampling distribution. The hypothesized mean is 40. The standard error was 1.25. When we found where 45 was, z was equal to 2.4. You know there's not going to be much left out there because that's over 2 standard deviations, or it's over 2 standard errors above the mean. The p-value, in fact, is this area down here in the tail. So if we take that z for 2.4 and just look that up, we'll get 4918, and 0.5 minus that is 0.0082. So this is the p-value. So to get the p-value, you have to draw your sampling distribution out, but then take the z-value that you calculated from the z-test and just get the area in the tail. In this case, in the upper tail. This is a one-tailed upper test. Remember, our HR, I'm going to go ahead and rewrite that, was mu greater than 40, and HO is mu equal to 40. Keep in mind, too, this sampling distribution that I've sketched here is the true sampling distribution you would get if HO was true. So if HO was true, that's what our sampling distribution would look like. So getting a value out here could happen if that was the real sampling distribution, but it would be very rare. Therefore, we think that the population mean isn't equal to 40, in fact, that it might be greater than 40. Okay, so 2 kind of approaches here when I'm asking this about what does the p-value tell you and what does it mean and all of that. At the most basic level, we will reject HO if p-value is less than whatever we used for a cutoff. And in this problem, if you look above on your paper, it says use a cutoff or an alpha of 0.05, a common level, but nothing magic about it. You can use any level you want, although there's implications for using different levels. But anyway, our p-value is equal to 0.0082. That is less than 0.05. Therefore, we reject HO and conclude mu is greater than 40. And you will get the same conclusion either method. They're just two sides of the same coin, two different ways to think and report about the hypothesis and the testing of it in this case. There's another part of this p-value, and this is one of those things where I'm going to say it, and I wish I hadn't erased everything, but I'm going to put that with 0.0082 was the p-value, and this was mu equal to 40, mu x bar equal to 40, and the x bar that we observed was 45. So again, remember I said this is the sampling distribution if, I should have said mu h over here. This is the sampling distribution if HO is true and if the population mean really is 40. So if mu is equal to 40, or if it were equal to 40, then there is a p-value chance, in this case a 0.0082 chance, of getting the statistic that we observed. It's a chance of getting an x bar. It's a chance of getting the statistic we observed, or one that's more extreme, further away from what HO is. A 0.0082 chance of getting x bar greater than or equal to 45. That's a small chance, which means that we probably will reject HO. In fact, we did just a minute ago. While we're on this, and I'll repeat this several times, I think it's one of the best analogies you can get. Let's say that you had a coin, and your HO is that you have a fair coin. Then you get 10 out of 10 heads, and let's just say that that's a really small probability, or a small p. So if the coin is fair, if HO is true, then there is a small p chance. I guess we could compute what that is, but right now I'm just going to say it's small, of getting the result that we had. We could say, well, 10 out of 10, or more than 10, or more than 9 if we were looking at some other number there, but something that extreme or more extreme. Of course, you really can't get more extreme than 10 out of 10 heads if you flip a coin 10 times. We're just going to create a confidence interval. You've seen confidence intervals before. It's like in a political poll, they'll say such and such candidate has 54% of the vote with a 3% margin of error. Basically, what we're doing with a confidence interval is getting or calculating a margin of error and making this into a confidence interval. Population standard deviation is 5. Sample of size 16. That means sigma x bar is equal to sigma divided by the square root of n is 5 divided by the square root of 16 is 1.25. The sample mean is equal to 45. Just continue on reading the problems now. And I have 90% confidence. If you look up in the table of common z values, for 90% you're going to see 1.645. So for a confidence interval, they all follow this basic formula. Statistic plus or minus a confidence coefficient. I'm just going to say z or t. Right now it's just z, but we'll get to t soon enough, times standard error. In this case, the statistic is x bar. I've already told you it's z in this case, and will be for a couple more days, times sigma x bar. Well, not just a couple more days. We'll introduce t in a couple of days, and then sometimes we'll have t and sometimes we'll have z. 45 plus or minus a margin of error of 2.056. For a lot of our purposes, it's better just to report the lower limit, that's 45 minus 2.06 to 47.06. I've just rounded that to 2.06.